it transferred mechanical vibrations from one clock to the other, making the two oscillators coupled. Huygens was the first to observe this kind of spontaneous synchronization in inanimate objects, and although he qualitatively described what was happening, it was only a few decades ago that scientists started fleshing out a rigorous theory of synchronization. You may have seen this demo where you put several metronomes on a light, wobbly platform and start them out of sync.
Just stay on.
It's trickier than people make it look. When you do get it to work, though, it's kind of magical. These metronomes don't have exactly the same natural frequency, and yet they still beat in time. To understand how this works, it's easiest to first consider a couple metronomes oscillating in sync with each other. When the large masses accelerate to the left, they push the platform to the right, and when they accelerate to the right, they push the platform to the left. So the center of mass of the system always stays roughly in the same spot. Now, if you start another metronome completely out of sync with the first two, the motion of the platform gives it a kick every half swing, speeding it up until it's in time with the first two. This works regardless of the number of metronomes you have. The platform just goes whichever way the majority of metronomes are pushing it. We can represent the position of a metronome pendulum or any other oscillator as a point on a circle. This shows its phase, that is, what part of the cycle it's in. So you could call the rightmost point of the pendulum 0 degrees, and then the leftmost point is 180 degrees. And as the pendulum oscillates back and forth, the point goes around the circle. The higher the frequency of the oscillator, the faster that point goes around. So this represents two metronomes with different frequencies, and this represents two metronomes with the same frequency, but completely out of phase. When the metronomes are synchronized in phase, their dots go around the circle together. We can use this depiction to illustrate a mathematical model for the synchronizing behavior we've been looking at. It's called the Kuramoto model. It says the rate each dot goes around the circle equals its natural frequency plus some amount related to how far it is from all the other dots. Now, the size of this term is determined by the coupling strength.
I like to think of it actually visually by thinking about people that are running around a track. Like suppose you're running with your friend, and maybe your friend is faster than you. Your friend says, come on, move it, hurry it up, because you're dawdling, you're slow, you're falling behind. So if you have enough fortitude and you try hard enough, and if the friend is sympathetic enough to slow down, then the coupling between you is strong enough to overcome that inherent difference in your natural running speeds. But if you're not very good friends, or if you can't quite suck it up to move yourself faster, then the coupling will not be strong enough to overcome that difference, and one person will start lapping the other.
The fireflies of Southeast Asia are apparently good enough friends because they synchronize their flashes. Even though each one has its own particular frequency at which it likes to flash, they couple to each other strongly enough so that hundreds, even thousands, can flash together in the same split second. There's a great simulation of this by Nicky Case,